Next up, Sorcha Manamon will talk about spatial distribution of CO in exocomet belt.
Hello, my name is Sorcha Manamon, and I am a final year PhD student in Trinity College Dublin, working with Professor Luca Matra. And today I'm here to talk about the ARKS large programme, in particular the spectrospatial distribution of CO gas we observe in exocometary belts. Sorry, how does it move? Oh, which one? Oh. Okay, perfect. Great. Okay, perfect. Solar system comets are very fascinating objects, and they are thought to be one of the reasons or one of the potential avenues for water having been delivered here into Earth. However, there's many difficulties with studying these objects in the context of volatile delivery into Earth. As these objects are very, very old, they're the same age as the solar system itself, so about 4.6 billion years old. And so during their lifetime, they have been heavily irradiated, they've been colliding with other objects, and so they have thermally processed over their lifetime. So they might have very different compositions now from the objects that once brought water into Earth. Luckily, we can observe exocomets in young nearby solar systems, and we can then use these exocomets to study the era of volatile delivery during the process of terrestrial planet formation. These exocometary belts, as Christine has mentioned, were once traditionally thought to be gas-free, and this was the defining difference between exocometary belts and debris disks. However, one of ALMA's greatest discoveries has been gas emission in over 20 exocometary belts. By studying this gas, it allows us to study the composition of these comets, though the origin is not known for all of the systems. The origin is either of primordial origin, which means it's left over from the protoplanetary disk phase, or it has been, or it is of secondary origin, which means it has been, or it is of secondary origin, which means it's come from the exocomets themselves. ARKS is the ALMA survey to resolve exo-Kuiper belt substructures, and it is the first ALMA large program to target these exocometary belts or debris disks. It's led by Seba Marino in the University of Exeter, and its co-PIs are Luca Matra and Meredith Hughes. The aim of this large program has been to study the diversity and the ubiquity of substructures in debris disks, and it's made up of 7 different teams around the world, each focusing on different aspects of the debris disk data. So some focusing on the dust, radial or vertical distributions, and others carrying out detailed collisional or dynamical modeling. My role within this large program has been to focus on the gas-rich debris disks. 5 of the original ARKS sample were known to be gas-bearing prior to ARKS. And so my role has been to image and characterize the gas in these gas-rich systems. And in the other remaining 13 systems in the original ARKS sample, my goal has been to carry out a search for CO gas in these disks, and in its absence, constrain upper limits on the amount of gas in each system. I should mention that the ARKS sample originally had 18 debris disks, and we have added 6 from the ALMA archive. So this total here is 24 disks. Here we have the 5 gas-bearing debris disks that were known to be gas-rich prior to ARKS. These are all A-type stars, all aged between 16 and 40 million years old, and they're all in the Scopus Centauri Association. These pre-ARKS images have resolutions of between 0.5 and 6 ARC seconds. My role within the project has been to develop a pipeline. So I've developed an imaging pipeline which uses Keplerian masking to guide the deconvolution of this large data. And with this, I have created high-resolution observations of these disks. Here we can see the moment zero maps, or the integrated intensity maps, of the 12 CO in each system. And as you can see, the gas in the disks are now resolved over many spatial resolution elements. From this data, I was also able to extract radial profiles of the gas in these exocometary belts. Here I'm showing the radial profiles for each of the systems in the 12 CO emission, which is in red, the 13 CO emission, which is in blue, and the black lines here show the millimeter-sized continuum, which is also observed through ARKS. As you can see in each system, the gas appears now to extend into the inner regions of the solar system as far as the inner resolution belt. The gas peaks interior to the dust in each system, and the gas is much broader than the dust in each system. What I'm showing here for the more face-on systems, so 49 SETI, 49 SETI, or HD 9672, 121617, and 131A35 are azimuthally averaged intensity profiles. But this process is not possible for the more inclined systems due to their very high inclinations. So as what I'm showing here for HD 32297 and 131A35 are the non-deprojected on-sky radial profiles. As I mentioned, there's many similarities with the systems, all of them having the gas peaking interior to the dust and being more broad, but we do see there is quite a variation from system to system with the differences between the gas and the dust. For example, with HD 121617, we can see that there's only a slight offset between the peaks of the gas and the dust, and this offset could be caused by just radiation pressure affecting the dust grains. However, in other systems, such as 49 SETI or HD 32297, the difference between the offset between the dust and the gas is too large to be explained by just radiation pressure, so gas drag may also be affecting the dust in this system. Using the radial profiles, I have been able to calculate a radially resolved 12 to 13 CO ratio in these disks. Up until now, we've been operating under the assumption that 12 CO in debris disks or exocometry belts is optically thick, 13 CO could be optically thick or thin, and a low 12 to 13 CO ratio would indicate optically thick gas. However, by studying how it changes with radius, we can make inferences to the optical depth of the gas in each system. 4 of these disks have radially flat 12 to 13 CO ratios within the error, and from this we can infer that the gas is either both optically thick or both optically thin everywhere they are detected within the system. My colleague Aoife Brennan has done extensive RADMC 3D modelling on HD 121617, and her results find that the gas in this disk is likely very optically thick, and so we believe it's likely the case for the remaining 3 gas-bearing exocometary belts. 49 SETI or HD 9672 is the only disk which we see the 12 and the 13 CO peak at different radial locations throughout the disk, and it's the only disk that shows what we would expect from an optically thick 12 CO being co-located with an optically thin 13 CO. This is also evident in the system's 1D profile, as we can see characteristics of an optically thick gas in the 1D profile for the 12 CO, but an optically thin gas for the 13 CO. Using spectrospatial stacking, I was able to measure the integrated line flux of the 12 CO in each system. To do so, for this, I did this to constrain the amount of gas in the gas-bearing debris disks, and also search for gas in the remaining 13 disks in the original ARK sample. Unfortunately, I did not find any gas in the gas-free disks, but I was able to constrain upper limits on the amount of gas in each system. I've combined those limits and those integrated fluxes here with any available ALMA observations or of the integrated flux for 12 CO. So we've observed the J3 to 2 line in ARKS. So I've used any available literature values for that. And I've also scaled any available 12 CO J2 to 1 lines as well by the average J3 to 2 to 2 to 1 ratio for every disk that has both lines observed. Here I'm showing the scaled line flux versus age, and as you can see, we are only seeing gas detected in younger debris disks, which is what we expected prior to ARKS. On the right here, I'm showing the scaled line flux versus the fractional luminosity. And what we're seeing here is that the more gas or the more dust we see in the systems, the more gas we're seeing as well. So this could indicate that a secondary origin for the gas in these systems. As the more dusty these systems are, the more gas we're seeing as well. So it could be that the same process that is creating the dust is also creating the gas. So I'll leave it here with my conclusions. With ARKS, we have improved very much so on the previous observations of the gas and the debris disks, and we're seeing very interesting structures between the gas and the dust, with a lot of follow-up to come. The first wave of ARKS papers have all been submitted. The first 4 of 10 have been accepted, including my paper on the gas observations. And so we're hoping that the rest of the papers which are currently under review or under revision will be accepted in the following months. So we'll be having the papers out by the end of the year. Finally, I am in my final year of my PhD. So if anyone has any postdoctoral funding coming up, I would love to chat. And yeah, I'll leave it there. Thank you very much and happy to answer any questions.
Thank you very much for the very interesting talk. Next speakers can come up and we'll take any questions. Okay, I'll take the speaker privilege and session privilege and then ask a question. So for the very the location between the dust and the detected CO gas, I saw there are a couple of systems where it's there's a very sharp edge of the inner and outer edge of the dust belt versus the CO. What idea could be explaining that sort of dissimilar distribution?
Yeah, so what could be happening if it's of a secondary origin could be that the gas is being released by the planetesimals and the millimeter-sized dust grains and viscously spreading outwards, which is what we would expect with viscous spreading from gas in these systems. But we can't really explain that just yet, as we need to know if there's shielding involved. We don't know if there's like H2 shielding the gas or if there's C1 shielding or CO self-shielding happening. So that's for follow-up observations.
Great, thanks. Are there any questions in the audience?
Hi, thanks for the great talk. Eric Van Klepper from the University of Chicago. I'm just curious if you have any information about the vertical extent of gas and dust in addition to the radial.
Yeah, so that's actually my next project. I've started working on HD 32297, which is, oh God, where is it? Here, this one here. So the vertical distribution of the dust is in its own ARKS paper. And so now my next project is to study how the vertical distribution of gas changes as well. So these discs 131488 and 32297 are perfect for that study because they're so edge on. And so right now we're seeing that the dust in this system is very well settled, but the gas is quite broad. So that's the next project to see why and what's happening there.
Okay. Thanks for all the questions and thank you, Sorcha. Okay, let's in the interest of time, let's move to the next speaker. Thank. Okay, our next speaker is Dingshan Dun, who will be talking about weighing disk mass with CO isotope logs.